Welcome to the Deep Dive. Today we're tackling a huge topic, something really shaping our future. Satellite megaconstellations. We've gone through your source stack, and the core conflict seems pretty clear. It's this massive trade-off. On one hand, you've got this promise of amazing, affordable internet for potentially, 400 to 600 million people who just don't have good access now. But on the other hand, well, there are some serious and growing environmental costs. We're talking the night sky, Earth's orbit, even our atmosphere. That's the tension we need to explore.
Absolutely. And the scale here, it's not theoretical anymore. It's real. It's happening right now. When we say mega constellation, we mean these coordinated fleets, usually 1,000 satellites or more, flying in low Earth orbit, LEO. Just look at Starlink. As of, say, September 2025, they've got something like 8,475 satellites up there. Most are working, maybe 8,460 or so. And they're already serving over 7 million users.
7 million. That number alone tells you this isn't niche anymore. Okay, so let's break it down. Why LEO? Why low Earth orbit? What's the big deal about being a few hundred kilometers up versus, the traditional satellites way out there?
Yeah, good question. It really comes down to two things: latency and physics. LEO is relatively close, I think 340 to maybe 1,200 kilometers up. Geostationary orbit, GEO, where the big old satellites live, that's 36,000 kilometers away. That huge distance means signals take time to travel back and forth. That's the lag, the latency you hate with slow internet. LEO cuts that down dramatically. We're talking speeds much closer to fiber optics.
Okay, so faster response times. What else?
Well, being closer also improves what engineers call the link budget. It's
Okay.
basically just a measure of signal strength. Closer means you don't need as much power, and the antennas on the ground and on the satellite can be smaller.
So it's faster and cheaper to talk to them. And the satellites themselves, they're built differently too, right? Mass produced.
Exactly. That's the other huge piece. Reusable rockets like SpaceX's Falcon 9/launch costs. And the satellites are built on assembly lines, more like electronics than bespoke spacecraft. Starlink is the prime example here. They even have lasers connecting the satellites, creating this mesh network in space. They're routing petabits of data daily up there. It's incredible.
A router network in space, that really paints a picture. So who are the main companies building this orbital internet? Where do things stand right now?
Well, there are definitely some major players. SpaceX Starlink, as we mentioned, is way out in front. They launch almost weekly, constantly putting up new satellites, moving to their Gen 2 mini designs. Then you have Amazon's Project Kuiper. They really started their big deployment push in April 2025. Their target is around 3,236 satellites.
So a direct competitor to Starlink on scale. What about the more established satellite companies?
Oh, right. Eutelsat OneWeb is another key player. They have about 650 satellites flying a bit higher, around 1,200 kilometers. Their focus seems less on direct-to-consumer broadband, more on enterprise, governments, airlines, shipping lines, that kind of thing. And we absolutely have to keep an eye on China's Guang. They've filed for nearly 13,000 satellites. Reports say they've launched about 72 so far, so early days, but the ambition is huge. Plus, there are these specialized players like AST Space Mobile and Link, focusing on something really disruptive, connecting directly to standard mobile phones.
Okay, let's stick with the upsides for a minute. The connectivity argument is powerful. Who benefits most?
Oh, it's potentially transformative for so many. Think about rural areas, the last mile where fiber is just too expensive to lay. Think developing nations, island communities. This offers them a path to modern broadband. And it's huge for mobility, too. Like United Airlines putting Starlink on planes for decent Wi-Fi at 35,000 feet. Same for cruise ships, remote work sites.
And we saw in Ukraine, didn't we, how vital this can be when ground infrastructure is damaged or destroyed.
Absolutely. Disaster resilience is a massive selling point. After a hurricane, an earthquake, you can deploy terminals and get communication back online fast. Ukraine really highlighted how a private satellite network can become critical infrastructure overnight for civilians and emergency services. And all this competition, it puts pressure on prices, which is good for consumers. Plus, mobile carriers are starting to see new opportunities, like offering satellite roaming packages.
That brings us neatly to this direct-to-phone idea, or DTC. You mentioned AST and Link. Starlink's doing it too. This seems like a fundamental shift. We're used to needing a special dish or terminal. How can my regular smartphone talk to a satellite hundreds of kilometers up?
It sounds like science fiction, but the tech is here. It's largely enabled by a mobile standard called 3GPP Release 17, NTN. NTN stands for Non-Terrestrial Networks. Essentially, they've figured out how to put a very sophisticated cell tower onto a satellite. These satellites have large advanced antennas that can pick up the weak signals from standard phones. The satellite handles all the tricky parts, like adjusting for the speed it's moving the Doppler effect so your phone just thinks it's connecting to a normal tower, albeit one moving very fast.
And this isn't just lab tests, it's actually rolling out.
Oh yeah, it's happening now. Starlink's direct-to-cell is live with T-Mobile in the US. They call it T-Satellite. They have over 650 dedicated D2C satellites up already. It started with text and some apps, but they're ramping up voice and data. AST Space Mobile has shown 5G voice and data calls using their huge Blue Walker 3 test satellite to regular phones. They've got partnerships with major mobile operators lined up. And Link Global is already offering commercial SMS services and emergency alerts in several countries. This basically eliminates the no-service dead zone, turning it into at least basic connectivity almost everywhere.
That is genuinely revolutionary. Okay, but we have to address the other side of the coin. Thousands, potentially tens of thousands of these bright, fast-moving objects in the sky. It can't come without consequences. Let's start with astronomy. The streaks.
Right, the visual astronomy problem. This is the most obvious impact for many people.
Mm-hmm.
Satellites, especially right after sunset or before sunrise, catch the sunlight while the ground is dark. They appear as bright streaks moving across the sky. For astronomers taking long exposure images of faint, distant objects, these streaks can ruin observations.
How bad is it for major projects? I saw mention of the Rubin Observatory.
It's a serious headache. The Rubin Observatory in Chile is designed for this huge, decade-long sky survey. Their projections estimate that potentially up to 1,000 images every night could be significantly affected by satellite trails once these constellations are fully built out. It fundamentally complicates their mission.
I know operators like SpaceX have tried things, painting satellites black, adding visors. Has that helped?
It has helped, yes. It's not a complete solution, but mitigations do make a difference. Things like darker coatings, designing satellites to be less reflective, and operating at lower altitudes, say 350 kilometers instead of 550, can reduce the brightness. Models suggest lowering the altitude could make trails about 6 times fainter. The target is generally to get them dimmer than magnitude 7, which is invisible to the naked eye. But even a dim streak is still a problem for sensitive telescopes.
Okay, so optical streaks are one issue. But then there's this newer concern, something about radio interference.
Yes, and this one might actually be more worrying in the long run. It's called unintended electromagnetic radiation, or UAMR. Think of it as electronic noise or radio leakage. Telescopes don't just see light, they listen for faint radio waves from the universe. Studies, particularly using the LOFAR radio telescope network in Europe, detected unexpected radio signals coming from Starlink satellites.
Wait, unexpected? They're licensed to transmit, aren't they?
They are, but in specific frequency bands Ku, Ka, V-band for communication, this leakage was detected in completely different bands, down around 110 to 188 megahertz. It seems to be coming from the satellite's internal electronics, the power systems, data buses, not the main communication antennas. It's like electrical static spilling out. And the problem is that 110 188 megahertz range is crucial for radio astronomy. It's used to study the early universe, cosmic dawn, fundamental science.
And I read something alarming in the sources that the newer Starlink satellites, the V2 minis, were actually worse.
That's what the LOFAR data suggested, yes. In some parts of that frequency range, the leakage from the V2 minis was detected as being up to 32 times brighter than the older V1 models.
32 times. That sounds potentially disastrous if you multiply it by thousands of satellites.
Exactly. This isn't about one satellite being noisy. It's about the cumulative effect. Thousands of these sources constantly orbiting could raise the overall radio noise floor of the entire planet, potentially drowning out those faint cosmic signals astronomers are trying to detect. It's why scientists are pushing hard now for international standards bodies, like CSP and the IEC, to set limits on this kind of unintentional emission from spacecraft, just like we have for devices on Earth.
Okay, so threats to optical and radio astronomy. What about the physical space itself? Orbital crowding, debris.
Yeah, this is the space traffic management nightmare. With thousands of satellites already and tens of thousands planned, LEO is getting crowded. Starlink satellites already account for the majority of close approaches situations where two objects pass potentially dangerously close to each other. Professor Hugh Lewis has done modeling suggesting that once the big constellations are fully deployed, they could be involved in something like 90% of all close encounters under 1 kilometer. Remember that incident back in 2019 when the European Space Agency had to manually steer their AOLIS satellite to avoid potential collision with a Starlink? That was an early warning.
In that low orbit, the thing that gives us low latency, it also makes them vulnerable, right? Didn't Starlink lose a batch of satellites recently?
They did, in February 2022. A relatively minor geomagnetic storm caused by solar activity increased the density of the upper atmosphere slightly. This extra drag was enough to cause 38 out of 49 newly launched Starlinks, which were still in a very low parking orbit, to re-enter and burn up. It showed just how slim the operating margins can be down there. A small change in space weather can have big consequences.
So things burn up, but we need rules for getting them down reliably when they're done, right? The old 25-year rule seems completely inadequate now.
Totally outdated. The U.S. Federal Communications Commission, the FCC, has brought in a much stricter 5-year deorbit rule for satellites licensed by them. They have to be disposed of within 5 years of finishing their mission. That's a huge improvement. But global enforcement is patchy, space law is complex, and not every nation has adopted such strict rules. And it's not without pushback. Amazon, for example, is currently challenging the FCC 5-year rule in court, so it's still evolving.
In managing all this traffic, you can't just send emails back and forth when thousands of satellites are involved.
No way. That's where automated systems come in. The U.S. Office of Space Commerce is developing something called TraCSS, the Traffic Coordination System for Space. It's currently in beta, but the goal is to provide automated, near real-time conjunction warnings, basically. Collision alerts, potentially cutting down notification times from days to minutes. That kind of system is essential for safety.
Okay, we've covered the sky, the orbit.
Yeah.
But there's one more area of concern, something more recent and maybe even more alarming, affecting Earth's atmosphere directly. Re-entry pollution.
Yes. This is the cutting edge of the environmental concerns, and it's deeply worrying. Re-entry aerosols. Satellites, especially the larger ones, contain a lot of aluminum in their structure. When they re-enter the atmosphere at the end of their lives, they mostly burn up. But the aluminum doesn't just vaporize harmlessly. It reacts with oxygen to form tiny particles of aluminum oxide, Al-Euro nanoparticles. Estimates suggest a typical 250-kilogram satellite might produce around 30 kilograms of this aluminum oxide dust upon re-entry. Wait, 30 kilos of nanoparticles per satellite? And we're talking about potentially thousands re-entering every year as constellations get refreshed. Where does all that dust go?
It persists in the upper atmosphere, the stratosphere, for a long time. And this is where the potential climate impact comes in. Early modeling, and this needs urgent verification with real-world measurements, suggests that if the total mass of re-entering satellites reaches about 10 gigagrams per year, which is plausible with multiple large constellations, these aluminum oxide particles could have serious effects.
So that's just...
Two main potential impacts. First, they could act as catalysts that deplete the ozone layer, potentially delaying its recovery. Second, they could absorb and scatter sunlight, potentially altering temperatures in the upper atmosphere, maybe by up to 1.5 degrees Celsius locally. It's a potential chemical contamination of the stratosphere on a global scale. NASA and NOAA are now really focusing on studying this.
And that's just the re-entry. The launches themselves have an impact too, don't they? They do. Even with reusable rockets, the sheer number of launches required means we're putting more emissions like soot and black carbon directly into the stratosphere, which also affects radiative balance and potentially ozone. So you have to look at the whole life cycle: launch, operation, disposal. It all adds up.
This really shifts the perspective. Let's zoom out to the bigger picture, the geopolitics. Ukraine showed these aren't just commercial services, they're strategic assets.
Absolutely. When a private company controls critical communications infrastructure, it gains significant leverage. We saw controversies around Starlink service being potentially restricted or geofenced in Ukraine. That dependence makes governments nervous.
Which explains why others are building their own.
Precisely. You see a major push for strategic autonomy. The European Union launched its IRS Constellation Initiative, aiming for about 290 satellites initially, specifically to avoid relying solely on U.S. providers. France and the U.K. are also bolstering Eutelsat OneWeb for similar sovereign capability reasons. Connectivity is now firmly a matter of national security.
But despite these national efforts, there's still no single global body managing space traffic or setting binding environmental rules.
That's the fundamental problem. The UN Committee on the Peaceful Uses of Outer Space, COPEUOS, has developed long-term sustainability guidelines, but they're voluntary. We rely on national regulators like the FCC, but their rules only apply to companies they license. There's no global treaty with teeth to enforce things like orbital debris mitigation or emission standards for everyone. It's a governance gap.
So given all these risks, astronomical interference, orbital debris, atmospheric pollution, geopolitical tensions, but also the undeniable benefit of connectivity, what's the way forward? What's the middle path look like?
Well, there are several pragmatic steps being pushed by both responsible industry players and the scientific community. First, making that 5-year deorbit rule the global norm, and crucially, demanding very high success rates for disposal, like 99% or better. Satellites must come down reliably. Second, establishing those technical standards. We talked about mandatory limits on radio leakage, UEMR, and maybe even satellite brightness, likely through bodies like CSPR and IEC. Third, fully implementing automated space traffic management systems like TraCSS globally. We need machines coordinating these thousands of objects.
And dealing with the junk that's already up there.
Yes, active debris removal, or ADR. We need to clean up existing debris and also design future satellites for easier removal. Missions like ESA's Clear Space One are testing technologies to capture defunct satellites. And initiatives like the Zero Debris Charter aim to get operators to commit to designing for disposal and removal by 2030.
Okay, so pulling it all together, it feels like we're at a real inflection point. We're getting this incredible global connectivity, truly a leap forward for potentially hundreds of millions. But the cost is a fundamental alteration of our near-Earth environment visually, radio-wise, and now chemically. It feels like we're treating space and the upper atmosphere as a resource to be consumed.
That's a good way to put it. And what you really need to watch is how quickly these environmental concerns, especially the atmospheric chemistry part, move from theory to policy. The reentry aerosol issue is potentially the biggest unknown, and it's escalating with every launch cycle.
So looking ahead, say over the next year or so, what are the key developments you'll be tracking?
I'd watch three main things. First, how Starlink's direct-to-cell service scales up with voice and data. That's when you'll really feel its impact in those dead zones. Second, Amazon Kuiper's launch cadence. Are they hitting their deployment targets? That will show how serious the competition is becoming. Third, and this is crucial but slower, watch for progress on those radio emission standards. The discussions leading up to the next World Radio Communication Conference in 2027, WRC 27, will be key. That could reshape satellite design.
And the traffic management system.
Right. Definitely watch NOAA's TraCSS. Seeing it move from a test system to being fully operational and widely adopted will be critical for managing LEOs safely as it gets even denser.
Okay, so to wrap up, here's the provocative thought we want to leave you with today. Considering the potentially serious but still uncertain impact of these aluminum oxide nanoparticles from satellite reentries on the ozone layer and upper atmosphere climate, how much data should we demand that operators collect during reentries about these atmospheric effects before we let them scale these constellations to tens of thousands of satellites? Should the burden of proof shift, requiring them to demonstrate atmospheric safety, not just orbital safety? If it does, the whole economics of the space race could change dramatically. Something to think about.